Okay, well, welcome back, everybody. I hope this was interesting and you had some success in first steps in T-Petra, creating a map and assembling a matrix. And I realized when we went through the rooms that some people had also some advanced questions. So I think this was, or I hope this was really interesting for many of you. With that, we move on to the third and final part of today, which is now assuming that we can assemble a matrix, and now it's all about solving the associated linear system. And for that, I'm happy to welcome Graham Harper from Sandia National Labs, who is an active Mueller developer, and he will introduce you to some basics of solving linear systems with preconditioned Rylov methods using Trilinos. Graham, and then of course his presentation will be followed by another exercise where you can actually look into how to do this yourself. Graham, yeah, the stage is all yours.
Thank you. Can you hear me?
Yes, very well.
Yep. Okay, perfect. That's right. So I'm going to talk about using Trilinos and application codes. And what we're going to focus on now is talking a little bit about how we would solve a Laplacian model problem and how we would do this with some of the different methods that we have available to us. So if you haven't heard of preconditioned gradient descent or Schwarz preconditioning, we'll talk a little bit about how these things work. Really, the scope of this is to now that you've assembled a matrix in the previous example with a T-Petra matrix, we're now going to look more at the choices of solvers and preconditioners in Trilinos that you have available to you in order to then solve the problem that you've assembled. And so this problem is oftentimes a linear system, and the way we write this is it's a linear system of the form AX equals B, where the matrix, of course, is A and your right-hand side vector B. And there are several different ways to do this within Trilinos. And this is where it's a little bit of kind of a large amount of information, because there's two different stacks available. If you haven't heard about this before, I think most of you are familiar at this point that we have the E-Petra and the T-Petra stack. The T-Petra, of course, being the more modern stack. You have many different choices as far as the route that you want to take. And so what I want to highlight is first that you have direct solvers available to you. And these direct solvers are packages such as a Mesos or a Mesos 2. Direct solvers, when you think of direct solvers, you should think of something like Gaussian elimination or numerical factorizations. Except really this package just does numeric factorizations, because something like Gaussian elimination takes, I think it's order of n cubed as far as complexity for solving a system. It's a lot of effort to solve a system, and it's one of the worst kind of direct solvers that you could use if you're looking at a large problem. So instead what we have is we have these various LU factorizations, incomplete LU, KLU. I think there's ILUT, and then of course these are all implemented in the various. There's KLU, UMPAC, SuperLU, Paradiso, MUMPS, and these are all various ways to then tackle your direct solve. However, these are still not. I wouldn't consider these to be scalable solvers. So the important thing to keep in mind is that solvers that are direct, while they give you the correct answer normally the first time, the important thing to remember is that the way they scale is not necessarily reasonable for large problems. And sometimes what you have to do is you have to also look at iterative solvers. And so there's a trade-off for each, but iterative solvers, really what it relies on, you have packages such as Aztec-OO, Balos, and these packages will solve your problem with something like conjugate gradient, biconjugate stabilized, GMRes, MinRes, and so on. this is something where you have your matrix and you have your vector. And the way you solve this iteratively is you do some clever applications of your matrix to your vector. You do matrix vector multiplies. If you've seen the power method before, think something like that, where you're taking the matrix and the vector and you're combining them in various ways in order to then construct a basis or to find coefficients to solve your problem. So you have really two different choices, but on top of that, you also have many, many choices for preconditioning. This is also the other thing that'll help with the scalability of your problem. So if your problem doesn't scale necessarily well to begin with, then you might also try to find some clever preconditioning techniques. Again, these things are available in both ePetra and tPetra stacks. And as you can probably guess at this point, if a package has a 2 on it, then you might think that this is kind of a more modern tPetra version of something. But you have ifpac and ifpac2, and ifpac and ifpac2 has a lot of different solvers, really. You can think of, again, ILUs, I guess, are in here, relaxation methods. When we talk about relaxation methods, normally this is something like Jacobi or Gauss-Seidel. This is something you might learn in kind of graduate level linear algebra, maybe undergraduate. But this is these are methods for solving your system. As they get more complex, you can have things such as the Chebyshev polynomials, which are then something else that you can solve with. But these are, you can use these solvers also as preconditioners. So that's the important thing, is that you can accelerate your solution by using methods such as these in various fashions. Multigrid methods are another good example of this, because multigrid methods are an optimal complexity preconditioner. I'll talk a little bit more about that on Wednesday when I talk about what the Mulu package does. But really the important thing is that you have many different approaches for multigrid, and this is either an ML, which is our kind of older multigrid package, or Mulu. And you have many different approaches for this. And within all of these different approaches, you can make choices about how you construct essentially basis functions for combining your degrees of freedom. So depending on your background, I think that if you know anything about multigrid, then I don't have to explain it. But if your background is in, or if you've heard about basis functions or things like that, I really think it's the easiest way to explain it. It's that you have your multigrid method essentially constructs basis functions, and you group degrees of freedom together, and then you continue to group. Once you construct those basis functions, you group those basis functions together and make more basis functions. And it allows you to make your problem much smaller, much more quickly. And so it's really a nice approach. There's also multi-level domain decomposition methods. And so in particular, we have Shilu, I believe, and Frosch. Let's see, is Alexander's name here? I believe Alexander works. Yes, yeah, his name's here, yeah. And so he works on Frosch, for example. So if you have questions about these sorts of things, then these are great questions to ask him. But I would think of these domain decomposition methods are methods where you solve your problem, or you do some sort of smart computations on a decomposition or a splitting of your problem. And these methods are also very powerful methods. And so to get started, what we're going to do is we're going to look at a Laplacian problem. And more specifically, we're going to look at a diffusion model problem. In this case, if we have a zero right-hand side, I guess we'd call it a Laplacian. If we have a non-zero right-hand side, you might also hear this called the Poisson problem. But the important thing is that we're going to have this minus, and then this operator here is the Laplacian operator, the divergence of the gradient. And it's of this scalar field U, and then we have a right-hand side. We're just going to do something simple where we have a scalar alpha, which is 1. so that we don't have to worry about any sort of changes in materials over space, and it makes it much more simple. Also, the domain's nice and simple. We're just looking at the unit square. And we're going to fix our boundary conditions to be 0. We're going to discretize it with finite element methods. And when we discretize it with finite element methods, ultimately what we end up with is a linear system of this form here. We're going to have this linear system Ku equals F. And with this Ku equals F system, we're going to then look at how we can solve it. Before we look at exactly how we solve it, one of the important things to keep in mind is that the way finite element methods work, for those of you who maybe aren't as familiar with finite element methods involve breaking your function down into basis functions. And when I say basis functions, I mean small piecewise functions, which are of a particular degree that you choose. These can be constants, linears, quadratics, cubics, and so on. We have a picture here in the top left, and this is in 2D. You can imagine what a basis function, which is piecewise linear, would look like. It's a little complicated at first if you haven't seen this before, but really the important thing is that in the center here, you have a point, and that center point is going to be where your function has a value of 1. It's going to reach the maximum there. And then as it goes down to all of the neighbors around it, it's going to go down to 0. So everywhere else on the grid, it's 0. What this does is this gives you something really nice to work with in several ways. One is, if you've seen interpolation theory before, you'll know that you can add piecewise linears together and reconstruct functions very easily just by taking the values at the points. So if you want to reconstruct a function and you know the values at each of the points, those are also the coefficients of your basis functions. It makes it very easy, and it's something that you may hear about again in the future. But the other important thing about these functions is that they have a small support, or they have a local support. And what I mean by that is they're non-zero in a very small area, and then they're 0 everywhere else. What that does is that allows you to then end up with a sparse linear system. When I say a sparse linear system, if you haven't heard this before, this is a linear system where there are a small number of entries per row. And so in this case here, if my function only is non-zero up to the, 6 points around it, then that means that my function only has a chance to really interact with about 6 functions that are neighbors to it. 7 if you count itself, because it also interacts with itself. So then what you could say is that this is a problem where I have at most 7 entries per row, because this basis function isn't going to talk to other basis functions on the other side of the domain. And this is especially nice. And again, the important thing which we'll highlight again is that with the superlinear complexity of direct solvers, it's okay to use direct solvers on simple problems. But if I were to make this mesh very fine, if I were to have a lot of degrees of freedom and a very large problem, then using a direct solver may not necessarily be the best choice for this sparse equation or sparse system of equations. So what we're going to do instead to kind of counteract that is we'll say that we want to use iterative solvers instead. Because for this given problem, we know some other nice properties about this. In particular, what we know is that the operator that the finite element method gives us is symmetric and positive definite. This is one of the very nice properties. It's variational properties of finite element methods, is that you have a symmetric positive definite matrix that you receive from the system. And so when you realize that you have these properties available, there's one method which has this requirement of symmetric positive definite matrices, which is the conjugate gradient method. We'll use this method to then solve our problem because this is the most restrictive method that we meet the requirements for. So in order to talk about this a little bit, I need to also talk about the convergence theory for the conjugate gradient method, because I think there's a couple important things to mention. We have this first theorem, and this first theorem tells us that the conjugate gradient method, which is an iterative solver, converges based on this error estimate here. This error estimate relates the error at step k to the error from your initial guess. So we're going to use E superscript k to represent your error after k iterations of the method, and E superscript 0 to represent the error of your initial guess. When you look at this error estimate here, you're going to see this kappa term, and this kappa term is the ratio of your eigenvalues. I'm going to let you think about it for a second. If I have a very nice matrix like the identity, what is my kappa going to be in that case? My kappa in that case, if I have the identity matrix, is going to be 1 over 1, which means my condition number is roughly 1. Now, if that number happens to be 1, this is the nicest matrix. Again, this is the identity matrix, so we're going to think that the identity matrix is something that you can solve immediately because you've solved all the variables. Then what does my error estimate tell me in this case? If it's 1, then my numerator for this becomes 0. This fraction in the first theorem, my numerator becomes 0. What does that mean if I plug that in? That tells me that my error at step k is less than or equal to 0. So that means that the conjugate gradient method, if your matrix is the perfect matrix, if it's the identity, and you have a condition number of 1, then this is going to be a convergence in 1 step, because after 1 step, you're going to then have an error of less than or equal to 0. And the only way you can do that is if you have the right answer, of course. Of course, things can get worse, though. What you could imagine is that this condition number, or how well your matrix is behaving, this number could get very large. In fact, you could think of problems, and we have an example underneath here where for the stiffness matrix, which is what we obtained from this finite element method, what you might actually end up with is you might actually end up with something scaling by the size of the elements in your mesh. And this is, if your elements are nicely shaped, this is going to look roughly like 1 over the size of your elements squared. If it's not a nicely shaped mesh, then it'll look worse. But the important thing is that this can get very bad very quickly. And so if your condition number is large, this should be something that tells you that you're going to have an issue with your solver, or that this is a difficult matrix to solve. And so again, I'm going to point at the first theorem and say, now if we have this equation and the condition number is very large, it goes to infinity, then what does that fraction in the middle become? As that number goes to infinity, that fraction in the middle is going to become very close to 1. When that fraction becomes very close to 1, what you're then going to see is that your error estimate is not actually improving or your error for your conjugate gradient method is not actually improving as your condition number is extremely large. And that's a problem for the method. So really what you should think about is that depending on how good your matrix is or how bad your matrix is, this number here will tell you roughly how much each step will reduce your error. And again, so down below what we have is this condition number, and this is really more of a theorem about finite element methods, which says that, again, if you have a mesh and H is the size of the elements in your mesh, then this is really something like it's something like 1 over H squared if your H and your minimum H are roughly the same. If they're not the same, then it could be much worse. And so the important thing is that this is going to deteriorate when you refine the mesh. So what we're going to do instead is we're now going to precondition it, and we're going to say, okay, now what I'd like to do is solve a different system which does have a nice matrix. I'd like to modify my original system and make it a nice matrix. If I make it a nice matrix, I can solve it more easily. The way we do this, so this is referred to as left preconditioning. I'm going to multiply the left by a matrix M inverse. And this M inverse matrix is a matrix which should roughly solve A. It doesn't have to be perfect. It doesn't have to be exactly A inverse. But the important thing is that this new system is still equivalent to the system you were trying to solve originally. But now you only have to worry about the properties of this M inverse A. Of course, if your M inverse A is exactly A inverse, this is the situation where your preconditioner exactly solves the problem, and it's maybe it's a silly example because then you have X and you've just solved for it already. But all of the cases in between, what you can have is you can have this case where you now have a matrix M inverse A, and you look at the condition number for that matrix. So we have this M inverse A, and if you look at the preconditioned conjugate gradient method, the error estimate looks exactly the same, now using the condition numbers for this instead. And this is very useful. This is, if you know a way to reduce the condition number of the matrix A by multiplying by something nicer or something that helps solve A, then that's extremely beneficial. And if you want to see what the algorithm for this looks like, here's a preconditioned conjugate gradient method. I'm not going to go into too many of the details at the moment. What I do want to point out is that since this is an iterative method, what you're going to end up doing is you're going to end up doing this repeatedly inside of a for loop or a while loop or something of that form. And the important thing is that you're constantly computing these things called residuals, which is B minus A times X. As long as you have that sort of concept and you understand how to compute these residuals, then really you understand the majority of the problem here, because you're computing these coefficients alpha, and then you're subtracting alphas times your previous steps, or alphas times information from your previous step. And then of course your preconditioner appears in here too. So you could look at something like a Schwarz preconditioner, which is sort of, you could think of this also as being constructed algebraically from the matrix by using ifpac or ifpac2, depending on whether you're in the ePetra or tPetra group. When we talk about Schwarz preconditioning or domain decompositions, what you should think of is restricting your problem to smaller domains. So this image in the top left, I have a red domain, a yellow domain, a purple domain, a blue domain. And what we're going to do is we're going to restrict to each of these domains, and we're going to solve that problem on the smaller domain instead. And the way we do this, we have R sub I and R sub I transpose. Those are called restriction and prolongation operators. And you should think of that as just restricting your problem to the domain or then including it back into the larger space again. And what you could say then is that related to this, then the way you can solve this is by combining your different domains that you solve into one larger solver. You restrict to a domain, you solve, and then you include back into the total domain. There's a condition number bound associated with this, and there's some other theoretical things to consider. But really, the important thing is just to talk about how we want to solve this. You can do this in Balos because Balos is based on the T-Petra stack. And you use something like a Balos solver factory to start things up. When I say SC, MV, and OP, these are template parameters. If you're a C++ wizard, you'll know what these, you would know what template arguments are at this point. If you haven't seen these much before, these are just one of the more complex features of C++, but it allows you to build code for any sort of scalar you can imagine. So if you want to use floats, doubles, longs, well, long's a bad example as a scalar, but the point is you can use many different types of, you can use many different types for your linear algebra, and you can do this as follows below. You can set some very, very small amount of information here, and you have a working solver. Again, if you want to then use a preconditioner with your problem, you can also do that by then passing in something called set right preconditioner to your linear problem. And once you do that, you can then tell the solver that you want to set the problem or to finalize the problem that you're looking at. Once you've done this, and of course, this also supports left preconditioning if you want to do left preconditioning. But really the important thing is that then if you want to solve the linear system after you've set everything up, the last thing you do is you just tell the solver to solve. And what it does is it returns a solve result. It'll tell you if it converged or if it did not converge. You can also use preconditioners from the ifpack2 package. And so using preconditioners from ifpack2, again, this is also using template parameters. And so the template parameters that we're looking at here, if you ever see SC, LO, GO, and NO, these are template parameters that refer to how you set up your problem for various scenarios that normally occur in supercomputing, but they can occur in other places as well. The important thing is that scalar type, again, tells you whether you're looking at floats or doubles or things like that. Local ordinals or global ordinals give you choices between things such as ints or longs or longs. This is especially important because as your problem gets larger and larger, if you have more than 2 billion variables, then you have to start worrying about what your global ordinal type is, because your global ordinal type is then incorrect. Your global ordinal needs to be something that can support 2 billion or more variables, and you have to change things like that. No corresponds to Cocos nodes, and this is also related to architectures and other concerns that you might have about working across various machines. But to set this up, all you have to do is specify a Tefos RCP to an ifpack2 preconditioner. Again, you're going to use these template parameters everywhere, this SCLO, GONO, and you create an ifpack2 preconditioner. If you want a relaxation preconditioner, you specify the string relaxation on your matrix. And if you want to then customize this even more and configure your solver, you can do so with a Tefos parameter list. You can specify the type of relaxation, the number of times that you relax, and the damping factor associated with the relaxation. Once you've done all of this, you initialize your preconditioner and you compute it, and that's how you feed it to your linear problem. Stratamikos is another way to do this. If you don't want to handwrite all of the code, then what you can do is go through Stratamikos. The really neat thing is that even though we're not actually, we're not covering it in today's tutorial, but Stratamikos is nice because you can use an XML input deck to then customize your solver. And there's a lot of complicated code that you have to use underneath. There's a lot of casting, and there's this package in Trilinos called Thyra that we use. But ultimately what you end up with is you end up being able to specify your solver like this without having to recompile your code. Some people may like this, some people may not like this. If this is something that's interested to you, I definitely would look into Stratamikos more. But with that, I think I'm on time. I should double check, but I believe this gives us time for the hands-on exercises now. And for the hands-on exercises, what we'll do is we'll solve a linear system with the now preconditioned Krylov solver based on this information we just looked at. And this is of course in the example 03 solve. And I think that's it.